I'm very flattered to be here. Walter Freeman has been one of my scientific heroes for several decades. I met him before this when we were both living in Amsterdam. And once I was honored by him reviewing a paper of mine, which I treasured the rejection letter for years afterwards. I'm going to break a little bit with the instructions today. I'm not going to talk about my work specifically that was influenced by Walter or that is run somewhat parallel to Walter. I'm going to talk about work of my friends. But I think you'll still see that this work is in some meaningful sense like derivative of Walter's work. I'll be talking about fractal time or 1 over f noise, and when I do that I'll be taking a snapshot of some work by Chris Kello. I'm going to talk about duality, not the dualism that Jay mentioned earlier, but a duality more in parallel with what people talk about in quantum mechanics, and in particular in emergent phenomena. And I'll also talk about something called tensegrity, which I learned about from my friend Mike Turvey, and I don't pretend to be expert in. I'm just kind of reporting a little bit on some work here today. There is an overarching theme, though, and that is that the self-organization of behavior is something that happens in a brain and a body. It matters that the brain is actually embedded in a body. And that's perhaps the part of the element that I want to elicit today from the perspective that I come to these problems. So first, let me introduce this idea of fractal time, or 1 over f noise. I think a lot of you already know about it, but if you look at the upper right hand of this slide, you see a kind of noisy-looking graph, and on the x-axis are trial numbers in an experiment, and on the y-axis are normalized reaction times. There are over 8,000 trials there. It's about 3 hours of sitting producing reaction times. And the interesting thing about data like this is it's that kind of weirdy, wavy pattern appears to be aperiodic, and yet we can take it apart. One way to take it apart, one way to look at this is with a spectral analysis. Using the unlimited power of linear tools, we can take this aperiodic signal and decompose it into periodic signals. What's interesting is with a robust range of decompositions, what you see is a relationship between the amplitude of the frequencies you pull out of this aperiodic signal and the frequency of those signals. So if you look at the line, that big red line in the lower right-hand side of this slide, you see these dots that are kind of grouping around that line, lining up, and you can actually see examples of the waves that are pulled out. The y-axis here is power or amplitude, and the x-axis is frequency, and lower frequency waves that are pulled out have much greater amplitude. Now, an interesting consequence of that is that means run your experiment longer, you're going to get a lot more variability. Variability is a product of the length of time you run the experiment. Now, this phenomenon has been observed in dozens of cognitive tasks. If there's some task that's your favorite in looking at cognition, an identification task, a categorization task, whatever, either it's been seen in that task or it's been seen in a cousin of that task. And it turns out to be actually quite difficult to make this go away, although you can kind of make it go away superficially. If you collect a little more data or you do your analysis a little more carefully, it turns out to yet be present in your data. We found it, we have not been able to make it go away. So it almost appears as though, as was suggested some time ago, that if you haven't found this fractal pattern, you just haven't taken enough data. You need to take some more data and look at lower frequencies. This kind of pattern is associated with self-organizing systems, metastable systems. Okay, so you get in this kind of range where you get to bring some other kinds of metaphors to the table, and you get to think about human behavior in slightly different ways. And one of the things that you think about is that behavior is extended in time. Now, this builds on a point that Mike Spivey just made about stimulation in time and behavior in time, but it also refers to a point Walter made yesterday, and that is that we tend to think of behavior as strictly reactive, and we kind of ignore the kind of preparatory work that goes into behaving. Like, for example, when I run someone in my laboratory, I have to tell them what we're going to do. And if they don't know what they're going to do, they don't do anything, okay? Or they do the wrong thing. So there's something about my instructing them and setting them up that prepares them to respond to tab. Now, what's cool about this way of thinking about behavior is that you start thinking like, well, maybe these measurements we're taking of behavior are rather arbitrary. I mean, when we say a reaction time, there's a built-in metaphor that what's interesting is the reaction of this system to a stimulus, not necessarily behavior. We're looking at a reaction, a punctate kind of thing. Well, Chris Kello quite cleverly got outside of this box and decided to expand the idea of measurement and behavior in some very interesting ways. Now, in his experiment, it's a rather simple thing. You say the word bucket, 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 to a metronome. And you say it hundreds of times, enough to get enough data for this kind of analysis. And then what Chris does is he takes that first bucket that you gave him, he breaks the syllables apart, he gets a buck and a ket, he runs a spectrogram on that and breaks that apart rather arbitrarily into different frequencies of that buck and frequencies of that ket. And he pulls out some of these frequencies arbitrarily, say 45 for buck and 45 for ket. And he looks at the amplitude at each one of those frequencies on that particular bucket, that first bucket that you produced. And then he takes those amplitudes and he goes through every one of your buckets, all the way out there, hundreds and hundreds of buckets. And he produces these data series at these arbitrary frequencies that you're seeing graphed up here. And this is a subset of the 45 that he would have taken for this particular subject on buck and on ket. So given this kind of arbitrary decomposition of speech, of repeated speech, he then does the kind of spectral analysis and other kinds of analysis, because you don't want to trust, when you're working with nonlinear fractal phenomenon, your linear tools come with certain qualifications, and so you actually need to have like kind of convergent operations here to deduce, see what you've got here really. And he does that, and what he sees is that all of these measures are fluctuating as 1 over F noise. So when you actually begin to dig a little deeper, like to look at the full complexity that is in behavior, what you see is that in every direction you're seeing this fractal pattern across time. In every measure you're seeing this kind of complex unfolding in time. So it can kind of create like some, look, if you were raised like me as a cognitive psychologist, it kind of kicks you in the head and you start rethinking, so what was I doing in my cognitive experiments? So Chris, as the way he describes this in a manuscript that's under revision, or perpetually under revision, that's like submitted again, is that first we recognize that this behavioral vested variation generally is fractal, long-range correlated. And the way Chris talks about this, that what we're seeing here is the evidence that the coordination of brain and body has its basis in this kind of metastable system, this kind of system that's poised at the right place between order and disorder so it can optimally react to its environment, change with its environment. Okay, so I'll go to my second topic now. Now I'm talking about work by John or Jay Holden at Cal State Northridge. So there's another perspective on these kinds of data. And that is, like, we're kind of used to thinking of these measurement events as punctate things. I run an experiment. I present a stimulus. I get a datum. Okay? It's like an event. It has some sort of isolable, it's a singularity. But it's not. It's part of a larger fractal pattern that's extending out to the boundaries of your experiment. Okay? Now, some of these experiments have been run over the course of a year and a half. And guess what? This boundary extends out to the full range of data collected across that experiment. I showed you a 3-hour experiment, and pretty much whatever scale we choose to start sampling behavior at, we see these patterns emerging. Well, one place in science where they confronted this kind of paradoxical duality before was in quantum mechanics, and I'm not going to at all get quantum mystical with you, but one of the things you do in science is you look someplace else and you say, well, how did they deal with it? What did that make them think about? And then where did they go from there? And so, well, this really kind of underdescribes what Jay Holden's been doing. you can kind of take quantum mechanics as kind of a metaphor, and you can use that to reconstitute the phenomena of human behavior, okay? And so you can actually start doing things. Now, what Jay is doing is actually testing a pretty an explicit model of 1/f scaling and behavior, of 1/f noise and behavior. But in one of his experiments, what he does is he does kind of a quasi-wave interference experiment, where he injects a kind of rhythmic perturbation into a reaction time experiment. So I've kind of illustrate, so on trial 3, he would go up to this poorly drawn sine wave, and he'd look over on the y-axis there, and he'd choose an interstimulus interval, and that would be the time between a fixation point and a signal to respond. And as the experiment progresses, he's got some frequency established here that's kind of oscillating across trials, and it goes from very short ISIs to very long ISIs and back again. And, okay. And we've known for a long time that ISI affects reaction time, and that's actually what Jay finds. Now, to read these panels, on your far left is a control condition, and on your far right is a control condition, and I'll kind of step through these. On the far left is just a reaction time with no wave interference in it, okay? It's just pretty much identical trials running reaction time, and that green line is giving you some sort of gauge of the scaling relation that's in those data. As we move to the right in the next panel, that red line is marking the frequency of the essentially interstimulus interval wave that Jay's put in, and he recovers that frequency, and it's additive. There's nothing changing in the scaling relation. The next panel over is a different frequency, and he recovers that frequency. The next panel over is those two frequencies added together, and he recovers the sum of those two frequencies. And in each of these panels, the wave that he's recovering is additive with the 1/f scaling, okay? In the rightmost panel is the other kind of control condition. That's where he takes the summed waves, randomizes their order. So now interstimulus interval is changing unsystematically from trial to trial. And now it actually interacts with the pattern of 1/f scaling, and the slope is getting closer down to white noise. Now, in other experiments he's done, when he does a randomized perturbation like this, he's actually played around with the amplitude of it, like how big that wave was that he's taking stuff from. And when he does that, he actually finds that the 1/f scaling is changing multiplicatively. So it's approaching the value of white noise, but it approaches it very slowly, okay, on a line on log-log scales as a function of the log of the perturbation that he's putting in, okay, or the amplitude of the perturbation. So on the one hand, this phenomenon behavior, variation behavior, can sometimes yield additive effects. We can recover the environment, this kind of smooth change of the environment in variation in behavior. On the other hand, unsystematic perturbations of behavior, as we would typically do in an experiment, are actually changing the underlying dynamics, or at least the only picture we're ever going to get of it in behavior, okay, and producing a different pattern. So, now the other clever thing that Jay did, actually inspired by some work that Chris Kello had done, instead of just looking at the key press response, he also looked at the time the finger sat on the key. So you've got one measure, reaction time, and another measure, just how long the finger sat there before it came up for the next trial. And as you move across, like now, and so these are interleaved measurements extending over the hundreds of trials of the experiment. So now as we look at key contact durations, again, you can compare that leftmost control condition with the conditions that are next to it as we move across the right. He recovers the same two frequency perturbations. He recovers their sum. But this time, in the randomized condition, it has absolutely no effect upon the slope of the 1/f scaling. Now, this is replicating an effect that Chris Kello had already demonstrated, that when you introduce a random perturbation, it will change the color of the reaction time scaling without changing the color of the key contact duration scaling. So these two interleaved series are somehow dissociated in, like, as they, although they extend through concurrent time across the experiment. So, okay. So one of our guides in doing these things was like a quote that Robert Schott at the University of Connecticut gave me in a course I took from him a few years ago. And that is to start thinking about measurement as a coupling of two systems. And so start thinking about what you're doing to people in laboratories as a coupling between that person and this artificial environment that you've just built for them. And once you start thinking that way, I mean, this is also like something that is a good description of what goes on in quantum mechanics. But we were kind of led to this working hypothesis that these measured values themselves are emergent. That is, measurement events, measurement outcomes, they differ in quality from this kind of micro world of the brain and body that we're measuring from. Okay, the last thing I'm going to talk about is this idea of tensegrity. I just want to give you a picture. This example will give you a little bit of a kind of more concrete picture of the body doing something, okay? Now, this tensegrity structure, this kind of a sculpture or toy, however you want to think about it, if you were to press down on it with your hand, okay, this thing, you can flatten it out, and then you let off in your hand, and it springs back to the original position. And that's because there is this actually balance of forces in this structure between, like, the tension structures in the cables and the kind of compression that's like, you know, the resistance to compression that's there in the struts. And that, with the speed of sound, like, transmits. Like, if you compress in one place, like at the speed of sound, that is transmitted through this structure. And so, like, you have this kind of, like, globally responsive structure. And as it turns out, that this kind of structure plays an important role in regulating cell biochemistry. The cytoskeleton of cells extending between the cytoplasm and nucleus actually has a lot of the structures in the cells arranged upon it, and those structures are actually, I mean, for want of a better word, triggered or regulated in their behavior by, like, compression on the cell. So if a cell is compressed equally on all sides, it commits suicide. It does cell death. And if a cell is stretched out, like what happens, say, when you have a wound or something like that, then that tensegrity structure is what turns on the growth that starts replicating that cell to help heal a wound and stuff. So tensegrity plays an important role in the behavior of cells. I couldn't find a cat or a rabbit, but I found a tensegrity hare. The idea here is that extending this metaphor from tensegrity out to the scale of organisms, that an organism also is, like, composed of these kinds of struts and cables, in that muscles and fascia, the way they're arranged on the skeleton, also have this kind of global, it preserves a kind of balance between the tension, the pull of the muscles and fascia, and the resistance to compression that's in the skeleton, and so you also have this globally responsive system. Now, so far everything I'm saying is there's a kind of an intuitive thing to this. I mean, it's like the first time I heard it, I thought, like, oh yeah, this sounds so cool. But of course, you'd also want to learn something new from thinking in terms of this way. And the interesting thing is that, you know, there's always been a puzzle about afferents from muscles and joints and stuff. For one thing, receptors are distributed too weirdly and kind of in the wrong places and too sparsely for them to be kind of working the way we've always kind of thought that the body was telling the brain what it was doing. But once you start thinking about it in terms of this tensegrity structure, and you look at where the receptors are actually sitting, they're sitting on the stress lines, okay, of the tensegrity object, okay, which allows the body to communicate across the body with the speed of sound what the whole body is doing, and allows this distribution of afferent receptors to keep the brain in the loop on where the body is and where how the body is situated with respect to the environment. And this is called the biotensegrity hypothesis as the basis of the haptic perceptual system by which the body and the environment adjacent to the body are perceived by the body. Okay? I want to thank my friends again for letting me talk about their work. The work I was talking about, none of it is published yet. Some appear in manuscripts, others have been talked about at conferences. But I thank you for staying so late today and for your attention. Yes.
Observation that within the brain also there are stretch receptors, because every time you turn your head or bend your neck, then this changes the shape of the brain. And when a person has a head injury, both injury with brain edema, then the swelling will change the spatial not dizziness, and it's not, let's say, loss of, it's a failure to know where the body is because of the alteration in the timing of the mechanism, which of course is based on lifelong experience. So this is, I think, a good example. I've never heard of that, but I think it's a marvelous concept.
Yeah. You know, I used to get these swelling things in my ears that like cause where like I'm just kind of sitting here and then all of a sudden the room seems to shift. I've come to wonder now if that kind of mechanical consequence of the swelling is involved in something like this. So. Well, we've done that, and you know, 1/f noise is itself rather unsystematic, and so what you do, you get is a widening of the 1/f scaling. So, like the intrinsic 1/f scaling, you're pulling out of the variability in behavior. If you're driving that with a stimulus that's actually driven by 1/f noise, the fact that it's also unsystematic, okay, works very much in the same way as if you're driving it with white noise. So, yeah.
When you talk about 1/f, you mean 1/f or
Yeah.
the exponent?
I mean 1/f as it's found in physiological systems and like natural systems. Yeah, I mean 1/f alpha is a mathematical construct, right? It's like a pure form of something, but empirically you actually see ranges that are differ from the -1. So. Yes.
In the 1/f, the power law course that you showed, I noticed something that we've seen. You do that on brain data, but it looks pretty linear over a wide range. There's always some kind of objective on it.
Yeah, that's.
What is that?
Yeah, that's actually in all cases of 1/f noise. You see that it's called Spanish moss by. I mean, Mandelbrot called it that, Spanish moss, and there are multiple sources. I mean, one is that you've always got processes that are oscillating on scales faster than the pace at which you're taking measurements. Now, they'll be aliased as white noise, and so they'll flatten the spectrum at that point. In some processes where you get really clean signals, you can actually use that, the point of inflection there to tell things about the system. In behavioral data, you don't get such a clean inflection, so it's kind of hard to know where that actually lives. But you actually, in physiological data, maybe you'd actually have cleaner.
Is there science about how it curves down at the end? Because there's been some papers on brain activity where they've not scale-free. Yeah, it's linear over a wide range, but then the way it falls off at the end apparently has some significance about whether it's truly scale.
In the high frequencies or in the low frequencies?
That would be like the right end.
Is that the high frequencies? Well, look, one issue exists in the low frequencies. I mean,
Is it just noise, kind of variation, or is there something functionally relevant?
well, it is noise. I don't know about functional relevance, but I do know that it's something you can manipulate. I mean, we put in different amplitude white noise. What we're doing is we're actually expanding that flat region as we bring down the slope of the 1/f. So I don't know of how you decompose white noise, and so I guess I would not. I guess I don't know about a theory of how things fall off there. I do know of a theory of on the other end of it, in the low frequency, if you see kind of a plateau up there, I mean that means you probably don't have 1/f noise. You probably have kind of short range correlations and then that's where you're hitting the characteristic scale of the system. So for example, in astronomy, there were many cases of wine bet on that they would eventually hit a plateau as they look at the structure of larger structure of galaxies and groups of galaxies. They haven't hit it yet. As they look deeper and deeper into space, there turn out to be even larger and larger structures arranged in a fractal pattern. But that wine still sits waiting for the plateau.
I think maybe one more. Go ahead.
I just have a quick, maybe my understanding is not fully correct, but I think applying that to an integration of the system. So if you take a x of t to x of omega, Fourier, you integrate x of t, it becomes 1 over f of x of f. And so if you have any system with noise in it, and if there's mass of a microphone or an RC circuit, it's just integrating over time, and you will get 1 over f out.
Yeah, there are actually many, many ways to curve fit or produce artificially 1 over f noise. And so, one of the questions you confront when you're dealing with this is like, is it legitimate in entertaining hypotheses like self-organization or metastability? As with any phenomenon, as with any area of science, okay, what you count on are predictions that come out of like the theoretical basis of it, and you go test those because there's no, we aren't supplied with phenomena that are like gold standards for our theoretical ideas. We're supplied with testable hypotheses. So.
Can I just say one thing about that?
Yeah, sure.
If you integrate white noise, you get brown noise, which is 1 over f squared. So you actually skip over pink noise. And that's why pink noise is always something special to physicists, for example, and engineers, because you can't just integrate white noise and get it.
Yeah, but what you can do is you can integrate like chosen frequencies, and you can smear them out a little bit with some white noise, and you can come up with like any particular example of 1 over f. You can come up with a facsimile. So,
that's probably time. So thank you.
Sure.